This lecture is about Cauchy sequences and proving that a sequence converges even when you don't know what the limit is. It's a technique somewhat copied off of what we did in proving the alternating harmonic series converges. So start off with a definition. We say a sequence AN is Cauchy if for every epsilon greater than 0 there is an n such that if little n and m are bigger than m, then the distance between a sub n and a sub m is less than epsilon. Note that in this case a sub n is an element of a sub n minus epsilon, a sub n plus epsilon for all little n bigger than capital N. Alright, so we're now going to prove that sequences converges if and only if they are Cauchy. So a sequence of real numbers converges if and only if it is Cauchy. And we break it down into two directions. We first assume that we have a series series AN that converges to A. And we'll show that it's Cauchy. This is the easy half of it. Let epsilon greater than 0 be given. Choose capital N so that if little n is bigger than capital N, then the distance between the limit and AN is less than epsilon over 2. Now suppose that n and m are both bigger than capital N. Alright. Now the distance between AN and AM is equal to, well, the absolute value of AN minus A plus A minus AM. So we added a 0 there. Now we apply the triangle inequality and now use our assumption, our supposition about n to see that AN minus A and AN plus minus AM are both less than epsilon over 2. Therefore, the distance between AN and AM is less than epsilon. Therefore, the sequence AN is Cauchy. Alright, now we're going to take the other direction. We're going to assume that it's Cauchy. Then we're going to construct a point to which the sequence AN converges, and then we'll prove that it does in fact converge to it. So we start off, and we're being very, very careful. I might read through this quickly, but I think it would pay you to pause and read the slide. So let's let let n sub 1 be chosen so that if little n and little m are bigger than n sub 1, then the distance between a sub n and a sub m is less than 1/2. And we let our first interval, I sub 1, be an interval that's centered at a sub n sub 1 and has a radius, shall we say, of 1. So a sub n minus 1, a sub n sub 1 plus 1 is our first interval. Okay. And if n is greater than or equal to n sub 1, then a sub n is an element of a sub n sub 1 minus 1/2 a sub n sub 1 plus 1/2, which is contained in I sub 1. So we're giving ourselves quite a bit of leeway on this, but because our control is a little floppy. We can't control around the center point that we're converging to. We have to control against these points that are sort of loosely connected with each other. Okay. Now our next step, we'll choose let n sub 2 be greater than n sub 1, so that if little n and little m are bigger than n sub 2, then the distance between a sub n and a sub m is less than 1/4. And I'll let I sub 2 be the interval, or a sub n sub 2 minus 1/2 a sub n sub 2 plus 1/2. Okay. So again, this is chosen so that it is contained inside of n sub 1. Okay. Now, if n is greater than n sub 2, let an be an element. Then an is an element of an sub 2 minus 1/4 an2 plus 1/4, and that's contained in I sub 2. And so we can continue this way, choosing each capital N subscripted bigger than the previous one and cutting the lengths in half. And so in this way we get a sequence of intervals so that they're nested within each other, and each subsequent interval is half as long as the previous interval. And so again, by the nested interval principle, there is a unique point A that is common to all of these intervals, and we claim that the sequence AN converges to A. Okay, now we'll show convergence. Let epsilon greater than 0 be given. Choose a k so that the length of I sub k is less than epsilon. Now suppose that n is greater than n sub k. Then A sub n is an element of I sub k, which is contained in A minus epsilon, A plus epsilon. Therefore, A sub n minus A in absolute values is less than epsilon. Therefore, it follows that A sub n converges to A. All right, having proven that, we're now going to do something that we will find very useful. It's called the divergence test. It says that if A is a series A1 plus A2 plus A3, if it converges, then AN converges to 0. So if the series converges, the sequence converges to 0. The converse of this is not true. But we use this to mainly if we have a series where the terms don't converge to 0, we prove that that series diverges. That's why we call it the divergence test. Okay. So let's suppose that we do have a series A that converges. Then A sub n is a sequence of partial sums. It's a Cauchy sequence. We wish to show that this A n converges to 0. So let epsilon greater than 0 be given. That there is a capital N such that if little n and little n are bigger than n, then the distance between AN and AM is less than epsilon. Okay, so now suppose that n is bigger than n plus 1. Then n and n minus 1 are both bigger than n. So the absolute value of AN is equal to a capital AN minus capital AN minus 1, and that's less than epsilon by our assumption, by our choice of n. Therefore, my series AN converges to 0.